Reality itself might be an illusion. The quantum world defies everything we think we know, from the solid ground beneath our feet to the very flow of time. We are about to explore 30 quantum anomalies that could shatter our understanding of the cosmos and rewrite the laws of physics. You will gain a new perspective on the fundamental nature of existence, seeing the universe not as a collection of separate objects, but as a deeply interconnected web. What happens when a single particle exists in two places at once? And why does observing it change its behavior? How can information seemingly travel faster than light? By the end, you will see the familiar world in a profoundly unfamiliar way. What part of your reality are you ready to question? Albert Einstein called it spooky action at a distance, a phrase that perfectly captures the deep unease this phenomenon caused him. He was deeply troubled by the idea that two particles could be linked in such an intimate dance that measuring one would instantly determine the state of the other, no matter how vast the distance between them. This is quantum entanglement, a connection so fundamental that the particles involved cease to have individual identities. They become a single, unified system, a ghostly pair sharing a single existence. For decades, this was a philosophical debate, a seeming flaw in the quantum theory that Einstein believed would be resolved. Then a physicist named John Bell devised a way to test it. His experiments and those that followed confirmed the impossible. The particles were communicating, or at least coordinating, in a way that defied any conventional explanation. They were not sending a signal through space. Instead, their connection seemed to bypass space entirely, as if the separation between them was an illusion. This violation of what we call Bell inequalities proved that the universe allows for correlations that have no classical counterpart. We have now sent entangled photons from satellites to ground stations hundreds of kilometers apart, and the spooky connection remains unbroken. This is not just a laboratory curiosity. It is the foundation for a technological revolution, promising unbreakable codes for quantum cryptography and immense power for quantum computers. But it forces upon us a far more profound question. If two particles can be one across any distance, what does that say about the nature of space itself? Is the emptiness between stars truly empty, or is it woven with invisible threads that bind the cosmos into a single, inseparable whole? This strange interconnectedness challenges the very stage upon which reality plays out, leading us directly to another baffling quantum behavior that occurs even when a particle is completely alone. But while entanglement reveals a mysterious connection between distant particles, a single particle alone presents a paradox just as profound. Think of a tiny electron fired toward a barrier with two narrow slits. If no one watches, it does not behave like a single, solid bullet. Instead, it acts as if it passes through both slits at once, creating an interference pattern of ripples, just like a wave in water. This is the heart of wave-particle duality. The very same electron can spread out like a wave and then suddenly appear as a definite particle the moment you try to measure its position. It exists in a blurred state of possibilities, a superposition of all potential paths, until an observation forces it to collapse into a single, concrete reality. This bizarre behavior was cemented by pioneers like Louis de Broglie, who proposed that every bit of matter has an associated wave with its wavelength tied to its momentum. We see its particle nature in effects like the Compton scattering, where photons knock electrons around like billiard balls, and we see its wave nature in classic experiments like Young's double slit, where light creates bands of light and dark. This is not just a theoretical curiosity. It is the operating principle behind electron microscopes, which use the incredibly short wavelengths of electrons to see details far smaller than any light microscope could ever reveal. So what does this mean for our everyday world? It suggests that the solid, predictable reality we experience is a kind of illusion, a frozen snapshot taken only when we look. The underlying fabric of the universe is a shimmering sea of potentiality, where things do not have definite properties until they are measured. This forces a staggering question. Does the act of conscious observation itself bring the world into being? As we confront the role of the observer, our attention turns to the seemingly empty space from which everything emerges. A ball rolling toward a hill should, by every classical rule, roll right back down if it lacks the energy to reach the top. Yet in the quantum realm, that ball can simply appear on the other side as if the hill were not even there. This is the magic and the profound anomaly of quantum tunneling. It is the bizarre ability of a particle to penetrate and pass through an energy barrier that it should have no possibility of overcoming. This is not magic, of course, but a direct consequence of wave-particle duality. Because every particle also behaves as a wave, its position is not a single point but a cloud of probability. This probability wave does not stop abruptly at a barrier. Instead, it decays exponentially inside the barrier. But if the barrier is thin enough, the wave, and therefore a finite chance of the particle itself, emerges on the other side. It is as if the particle simply cheats, taking a forbidden shortcut through reality itself. This phenomenon was key to unlocking one of the great mysteries of radioactivity. The physicist George Gamow used it to explain alpha decay, where an alpha particle escapes the powerful nuclear force holding it inside an atomic nucleus, a feat it should not have the energy to accomplish. Gamow showed that the particle is not climbing out, it is tunneling out. This single insight revealed that the cores of stars, including our own sun, are powered by this quantum defiance. Protons in the stellar core, repelled by their mutual positive charge, should never get close enough to fuse, but they do not need to collide with brute force. They simply tunnel through the electrical barrier that separates them, enabling the nuclear fusion that makes stars shine and life itself possible. Here on Earth, we have harnessed this quantum trick for our own technology. The scanning tunneling microscope drags a tiny tip across a surface, and electrons tunnel across the gap between the tip and the atoms. By measuring this tunneling current, we can map the surface atom by atom, making the invisible world visible. Even within our own bodies, enzymes use quantum tunneling to speed up essential biochemical reactions, transferring particles in ways that classical chemistry cannot explain. So this is not a minor oddity. It is a fundamental process that shapes our universe from the largest stars to the smallest life. It forces us to ask if particles can ignore barriers and appear where they are forbidden to be. What other impossibilities are merely probabilities waiting to be realized? This defiance of classical limits opens the door to an even stranger idea, a state of being that challenges the very concept of a single, stable reality. The defiance of classical barriers we see in tunneling is only possible because of a far more fundamental strangeness. A particle is not merely hidden before we look, it exists in a blurred state of all its possible realities at once. This is quantum superposition, a concept made famous by Erwin Schrödinger's unsettling thought experiment of a cat sealed in a box. In this scenario, the cat's life is tied to a random quantum event, like the decay of a single atom. According to the rules of the quantum world, until someone opens the box and looks inside, the atom is in a superposition of both decayed and not decayed. And therefore, the cat is suspended in a state of being both alive and dead simultaneously. This was not meant to be taken literally, but to highlight the apparent absurdity of applying quantum rules to the large-scale world we see. Yet for a single particle, superposition is an undeniable fact. An electron does not have a definite position or spin until it is measured. It occupies a combination of all its possible states, a condition described mathematically by Schrödinger's famous wave function. This wave function is not a physical wave in water or air, but a wave of probability, a mathematical object that contains all the information about what could happen. It exists in an abstract realm of infinite possibilities known as a Hilbert space. The moment a measurement is taken, this delicate superposition collapses. The countless possibilities vanish, and a single, definite reality is all that remains. This is the core of the Copenhagen interpretation, the standard view of quantum mechanics for decades. But how does this bizarre property move from a philosophical puzzle to a world-changing technology? The answer lies in the heart of a quantum computer. A classical computer bit can only be a 0 or a 1. A quantum bit or qubit can be 0, 1, or any complex combination of both at the same time, thanks to superposition. This means that 2 qubits can represent 4 states simultaneously, 3 qubits can represent 8, and so on. With just 300 qubits, you could, in principle, represent more states than there are atoms in the known universe. This exponential power allows quantum algorithms to explore a vast number of solutions to a problem all at once. A famous example is Shor's algorithm, which uses this principle to factor enormously large numbers, a task that would take a classical computer longer than the age of the universe. This capability could break most of the digital encryption that secures our modern world, from online banking to private messages. Other algorithms use superposition to solve fantastically complex optimization problems, like finding the most efficient routes for global shipping or designing new life-saving drugs by simulating molecular interactions directly. This forces a deep philosophical question. If the fundamental components of reality are not deterministic, if they are governed by probability and only become real when observed, what does that say about cause and effect in our own lives? Does the universe have a predetermined path, or is it being written moment by moment? The answer to how this fragile world of possibilities gives way to our solid, single reality may lie in the process that constantly destroys superposition all around us, a phenomenon known as quantum decoherence. The pristine melody of a quantum superposition cannot survive in a noisy world. This gradual fading, this loss of a particle's magical ability to be in multiple states at once, is known as quantum decoherence. It is the reason why a baseball never exists in 2 places at once, and why Schrödinger's cat is never truly both alive and dead. The quantum world is incredibly fragile. For a particle to maintain its coherent superposition, it must remain perfectly isolated. But complete isolation is impossible. The instant a quantum system interacts with even a single photon from its environment or a random air molecule, it becomes entangled with that outside world. This entanglement is like a leak. Information about the particle's state spills out into the environment, and in doing so, the delicate superposition is destroyed. The system decays into what physicists call a classical mixture, a simple either-or. It is not that the particle chooses a state, but that its quantum weirdness is overwhelmed, like a single voice being lost in a roaring crowd. This process happens at lightning speed. For a large molecule, decoherence can occur in mere femtosecond, a fraction of a trillionth of a second. For smaller, more isolated systems, like a carefully trapped electron, the coherence can last longer. Physicists like Wojciech have shown how this explains the transition from the quantum to the classical realm. Certain states, which he called pointer states, are more robust and resistant to this environmental noise. These are the states we consistently measure, the definite positions and properties we see in our everyday world. Decoherence provides a powerful answer to the measurement problem. The wave function does not need a conscious observer to collapse. It collapses constantly, everywhere, simply through contact with the environment. This understanding is not just philosophical. It is the central engineering challenge in building a quantum computer. Qubits are exquisitely sensitive, and their superpositions must be protected long enough to perform calculations. This is why quantum computers are housed in elaborate, ultra-cold refrigerators, shielded from the slightest thermal vibration and electromagnetic whisper. The entire field of quantum error correction is a desperate battle against the relentless tide of decoherence, a fight to preserve a quantum state against the encroaching classical world. So the solid reality we experience is not an illusion. It is the inevitable outcome of a quantum system interacting with itself. Our classical world emerges from this constant, quiet measurement performed by the universe itself. But if our reality is built upon this fragile quantum foundation, what is the nature of the stage it sits upon? The answer may lie in the seemingly empty space from which everything emerges, the mysterious quantum vacuum. The quiet emergence of our classical world from quantum decoherence hints at a hidden structure beneath it all. Even the emptiest void in the universe is not truly empty. It seethes with a ghostly energy, a restless foam where particles and their antimatter twins spontaneously wink into existence, only to annihilate each other an instant later. This is the quantum vacuum, a state of pure potential that defies our deepest intuitions about nothingness. This bizarre activity is a direct consequence of Werner Heisenberg's uncertainty principle. This principle tells us that for extremely brief moments, the strict conservation of energy can be temporarily violated. The vacuum borrows energy from nowhere, creating these virtual particle pairs, and then repays the debt so quickly that the violation is undetectable. The theoretical foundation for this was laid by Paul Dirac, whose quantum field theory described the vacuum not as a passive void, but as the lowest possible energy state of a field, a state that is still buzzing with this transient activity. We can even witness the effects of this quantum seething. Place two uncharged, perfectly smooth metal plates extremely close together in a vacuum. Classically, nothing should happen. But in reality, the plates will be gently pulled toward each other. This is the Casimir effect. The space between the plates restricts the kinds of virtual particles that can pop into existence, while the space outside does not. The greater pressure from outside pushes the plates together, a tiny but measurable force born from the activity of nothing. These fluctuations are not just theoretical curiosities. They leave their fingerprint on the very building blocks of matter. In the fine structure of atomic spectra, a small shift in the energy levels of electrons, known as the Lamb shift, occurs because electrons are constantly jostled by these virtual particles flickering around them. This subtle effect confirmed the reality of the quantum vacuum. Its implications stretch to the grandest scales of all. In the first fleeting moments after the Big Bang, the universe is thought to have undergone a period of incredibly rapid expansion called inflation. During this time, the microscopic quantum fluctuations in the vacuum were stretched to astronomical sizes. These tiny ripples in the fabric of spacetime became the gravitational seeds for everything that followed. The vast cosmic web of galaxies, the clusters and the voids, are all the magnified echoes of those primordial quantum whispers. This leads to a staggering possibility. The vacuum energy, this baseline energy of empty space, might be the very engine driving the accelerated expansion of the universe, a phenomenon we attribute to dark energy. What we call empty space may be the most dominant and mysterious component of our reality, its subtle quantum jitter holding the key to the ultimate fate of the cosmos. But if the vacuum itself is alive with instantaneous creation and destruction, what does that say about the nature of connection across the universe? This brings us back to a deeper mystery, the enigma of quantum non-locality. The ghostly connection of entanglement points to a truth far stranger than mere correlation. This is the anomaly of quantum non-locality, the unnerving realization that the universe can link distant events without any signal passing between them. It is as if two dice thrown in separate galaxies always land showing the same number, not because they are communicating, but because their fates were always one. The theoretical foundation for this was laid in a famous challenge known as the EPR paradox, conceived by Einstein, Podolsky, and Rosen. They argued that if quantum mechanics was correct, it implied this spooky action at a distance, which they believed was proof that the theory was incomplete. They proposed that there must be local hidden variables, unseen factors that predetermined a particle state, preserving a sensible, local reality. For decades, this was a philosophical stalemate. Then physicist John Stuart Bell found a way to break the deadlock. He devised a mathematical theorem, now known as Bell's theorem, which set a clear limit. If local hidden variables existed, the correlations between entangled particles would never exceed a certain value. Quantum mechanics, however, predicted those limits would be shattered. The baton was passed to experimenters like Alain Aspect, who created incredibly precise tests. Their results were unequivocal. The quantum predictions were correct, and the Bell inequalities were violated. The universe had chosen the spooky path. Measuring the spin of one entangled photon here on Earth instantly determines the spin of its partner, even if that partner is on the far side of the moon. This influence is instantaneous, seemingly faster than light. Yet, and this is the crucial saving grace, no usable information is actually sent. You cannot force the distant particle into a specific state of your choosing, so you cannot send a message faster than light. Einstein's theory of relativity, with its cosmic speed limit, remains intact. This paradox, where influence is instantaneous but communication is not, forces us to reconsider the very nature of space and time. Perhaps they are not the fundamental stage of reality, but emergent properties of a deeper, interconnected quantum whole. This profound interconnectedness is not just a cosmic curiosity. It is the engine of quantum teleportation. In this astonishing protocol, the non-local link between two entangled particles is used as a resource. By performing a specific measurement on one particle entangled with another, and then sending some classical information to a third location, the quantum state of a particle can be disassembled here and reassembled there. The particle itself is not traveling. Its unique quantum identity is being transmitted using the invisible bridge of non-locality. This is the foundation for a future quantum internet, where information security is guaranteed by the laws of physics themselves. So what is the true fabric of our reality if separateness is an illusion? This question pulls our focus to a more intrinsic property of the particles that make up this web, a property as fundamental as it is bizarre: quantum spin. This intrinsic property of spin is not a rotation in any ordinary sense. An electron is a point-like particle with no physical size to spin at all. Yet it possesses this fundamental quality called quantum spin, a form of intrinsic angular momentum that is forever fixed and quantized. Think of it not as a spinning ball, but as an innate magnetic orientation, a tiny arrow pointing in a specific direction. When you try to measure its orientation along any given axis, you do not get a smooth range of possibilities. The result is always one of two discrete values, up or down. This bizarre quantization was stunningly demonstrated by Otto Stern and Walther Gerlach. They shot a beam of silver atoms, each with a single unpaired electron, through an uneven magnetic field. If the electrons were like tiny classical magnets, the beam would have smeared out into a continuous band. Instead, it cleanly split into two, and only two, distinct beams. The universe at its core operates on a digital code of discrete possibilities. This binary nature of spin, especially for particles like electrons which have a spin of 1/2, makes them perfect candidates for the qubits at the heart of quantum computing. An electron spin up can represent a 0, spin down a 1, or any ghostly superposition of both, but the implications of spin go far deeper than technology. It was Wolfgang Pauli who uncovered one of its most profound consequences, the Pauli exclusion principle. This rule states that no two identical fermions, the class of particles that includes electrons, protons, and neutrons, can occupy the exact same quantum state. This means that if two electrons are in the same orbital around an atom, they must have opposite spins. It is this single, simple rule that prevents all the electrons in an atom from collapsing into the lowest energy level. It forces them to stack into higher and higher shells, building the complex architecture of the periodic table of elements. Without the Pauli exclusion principle, there would be no chemistry, no variety of matter, no complex structures, and no life. The very diversity of our material world rests upon this single quantum rule. We see its effects in the magnetic world around us, from a simple refrigerator magnet to the hard drive in your computer. The alignment of countless electron spins creates the magnetic fields we harness every day. Even in the subtle dance within an atom, an electron spin interacts with its orbital motion around the nucleus, a phenomenon called spin orbit coupling that fine-tunes the light atoms emit and absorb. And on a larger scale, we use this knowledge to peer inside the human body. Magnetic resonance imaging, or MRI, manipulates the spins of hydrogen nuclei in water molecules. By tuning radio waves to the precise frequency that makes these spins flip, we can map their density and location, creating breathtakingly detailed images of our soft tissues without a single cut. So this strange, non-classical spin is woven into the fabric of everything we are. It dictates how atoms bond, how materials feel, and even how we see inside ourselves. What does this fundamental binary nature of particles reveal about the underlying symmetries of the cosmos? The answer may lie in how we can use this property to move information itself across the void, guiding us to the next great anomaly, the promise of quantum teleportation. The strange binary nature of quantum spin provides the perfect language for a far more astonishing feat. Quantum teleportation makes it possible to transfer the exact quantum state of a particle to a distant location without physically sending the particle itself. This is not science fiction. It is a direct application of the spooky connections we have already witnessed. The entire process hinges on a pre-established pair of entangled particles. Imagine you have three particles. Particle A is the one whose unique quantum identity you want to teleport. Particles B and C are the entangled pair, with B staying with you and C sent off to your friend across the galaxy. The magic begins when you perform a special joint measurement on your particle A and your half of the entangled pair, particle B. This is known as a Bell state measurement. This act instantly links particle A with the entangled system. Because B and C were already one quantum entity, this measurement forces particle A's quantum information to be imprinted onto the distant particle C. But there is a catch. This process also scrambles the original state of particle A, and the person holding particle C cannot yet use it. the final, crucial step requires you to send a simple, classical message to your friend. This message, sent at the speed of light or slower, contains the instructions for how to perform a specific rotation on particle C. Only after applying this correction does particle C become a perfect replica of the original particle A. This two-step dance, a blend of instantaneous quantum influence and slow classical communication, is what makes teleportation possible without violating relativity. A fundamental rule of the quantum world makes this all necessary, the no-cloning theorem. It is impossible to create an identical copy of an unknown quantum state. You cannot simply scan a particle and make a duplicate. Teleportation cleverly circumvents this by always destroying the original in the process, ensuring that only one perfect version of the quantum state exists at the end. Since the first proposal by Charles Bennett and his team in 1993, this has moved from theory to laboratory reality. Scientists have successfully teleported the quantum states of photons across distances exceeding 100 kilometers, both through optical fibers and through the open air between ground stations and satellites. This is the foundational technology for a future quantum internet, where information security would be guaranteed by the laws of physics themselves. Sensitive data could be transmitted with absolute certainty that any eavesdropper would leave a detectable trace. How could this transform our world? It promises a network where quantum computers can be linked together, creating a global web of processing power capable of solving problems we cannot even conceive of today. It forces us to ask a profound question about the nature of information itself. If the essence of a particle can be disembodied, transmitted, and reassembled elsewhere, what truly defines an object? Is it the stuff it is made of, or the information that describes its quantum state? This manipulation of quantum information reveals a deeper layer of order in the universe, a precision so exact it can be used to redefine our most fundamental standards of measurement, as seen in the next great anomaly. The precise manipulation of quantum information reveals an even deeper order in the universe, a perfection so exact it can redefine reality itself. Picture a flat, two-dimensional world, a layer of electrons trapped like a puddle, and then subjected to an immense magnetic field at temperatures near absolute zero. Under these extreme conditions, something magical happens. The electrons stop behaving like a chaotic gas and organize into a new state of matter, giving rise to the quantum Hall effect. Discovered by Klaus von Klitzing, this phenomenon revealed a stunning truth. The electrical resistance of this two-dimensional electron gas does not change smoothly. Instead, it leaps between distinct, perfectly flat plateaus. The value of this Hall resistance is quantized, taking on only specific values that are integer multiples of a fundamental constant, E squared divided by h. The precision is so absolute, so immune to imperfections in the material, that it has been used to redefine the international standard for electrical resistance. This is not a mere laboratory measurement. It is a window into a hidden mathematical perfection woven into the fabric of our universe. How can such perfection emerge from chaos? The answer lies in how the magnetic field forces the electrons to move. The field confines them into discrete, quantized energy rings called Landau levels. In a perfect, infinite sheet, the resistance would follow a smooth curve, but in a real, finite sample, something else occurs. The electrons in the bulk of the material are trapped, orbiting in circles. However, at the very edges, they can only move in one direction, creating robust one-way highways known as edge states. These edge channels are the key to the effect's astonishing precision. They are protected from scattering by the material's internal disorder, making the measured resistance depend only on fundamental constants of nature. This robustness points to a deeper property known as topology, a kind of mathematical fingerprint that remains unchanged even if the material is stretched or dented. The integer quantum Hall effect was just the beginning. Later, an even stranger version was discovered, the fractional quantum Hall effect. Here, under stronger magnetic fields, the electrons condense into a collective quantum fluid. Within this fluid, the fundamental excitations are not individual electrons, but quasi-particles carrying a fraction of an electron's charge. Robert Laughlin provided the theoretical key, explaining how these fractional charges emerge from the complex correlations of the electron sea. This discovery opened the door to the study of anyons, exotic quasi-particles that are neither fermions nor bosons. When two anyons are swapped, their quantum wave function changes in a way that is subtly different from a simple sign flip, a property that could make them the perfect, fault-tolerant qubits for topological quantum computers. So what do these perfect, quantized steps tell us? They whisper that beneath the apparent complexity of our world lies a profound mathematical elegance, a universe that counts in precise, unchangeable integers and fractions. But this perfect order raises a new question. What happens when this delicate quantum system is pushed toward the brink of chaos? The pristine order of the quantum Hall effect exists at one extreme of a vast spectrum. Yet the quantum world has another face, one of wild unpredictability and intricate disorder. This is the domain of quantum chaos. In our everyday world, chaos is familiar. A tiny puff of wind can send a rolling pencil into a wildly unpredictable path. This is deterministic chaos, where a system's future is exquisitely sensitive to its starting conditions. But what happens when such a system is shrunk down to the quantum scale? Consider a single particle trapped inside a stadium-shaped enclosure, a so-called quantum billiard. Classically, a ball in such a stadium would bounce off the walls in an orbit so complex and sensitive that its future path becomes essentially unpredictable after just a few collisions. In the quantum version, the particle is described not by a trajectory but by a wave function. These wave functions do not form neat, orderly patterns. Instead, they erupt into fantastically complex, lace-like structures with peaks and valleys distributed in seemingly random, unpredictable ways. The chaos of the classical motion is imprinted onto the very fabric of the quantum state. How can we possibly quantify this? The key lies not in the wave functions themselves, but in the spectrum of the system's possible energy levels. For a quantum system that is classically regular, like a particle in a circular box, the energy levels are spaced in a somewhat predictable, correlated manner, following what is known as a Poisson distribution. But for a quantum system that is classically chaotic, this order shatters. The energy levels begin to repel one another. They avoid getting too close, as if each level demands its own personal space. This statistical pattern of level repulsion is perfectly described by random matrix theory, a branch of mathematics developed to model the energy levels of complex atomic nuclei. This connection, proposed by physicists Oriol Bohigas, Marie-Jeanne Giannoni, and Charles Schmidt, became known as the BGS conjecture. It suggests that the fingerprints of classical chaos are universal, appearing in the quantum statistics of systems as diverse as heavy atoms, complex molecules, and nanoscale devices called quantum dots. In these tiny semiconductor structures, the flow of electrons is dramatically altered by the underlying chaotic scattering of their wave functions. Sometimes, a bizarre ghost of order remains. Even in a chaotic system, certain wave functions can become pinned or scarred along the path of an unstable classical periodic orbit. It is as if the quantum particle remembers a trace of a path it should have long forgotten. This discovery, largely advanced by Martin Gutzwiller through his trace formula, provides a bridge. It connects the deterministic but unpredictable world of classical chaos with the probabilistic and indeterminate quantum realm. So what does this mean for our reality? It reveals that chaos is not just a feature of the large-scale world. It is woven into the quantum fabric beneath it, influencing how energy is distributed in nuclei and how electrons flow in the microchips of the future. This interplay between quantum law and chaotic motion pushes us to consider an even more extreme environment, where the laws of quantum mechanics meet the ultimate chaotic system, a black hole. This brings us to a faint whisper of heat from the abyss, the anomaly of Hawking radiation. Even in the deepest abyss, a faint heat flickers into existence. The most absolute prison in the universe, a black hole, is not entirely black. It glows, and in doing so, it slowly vanishes. This is Hawking radiation, a phenomenon that forces the laws of the very large and the very small to finally meet. Stephen Hawking's great insight was to ask what happens when you bring quantum field theory to the edge of a black hole's event horizon. We have already seen that the vacuum of space is not empty, but a seething foam of virtual particle pairs popping in and out of existence. Normally, these pairs annihilate each other almost instantly, but at the very precipice of an event horizon, a gravitational point of no return, something different can occur. One particle of the pair might fall across the horizon while the other escapes into the cosmos. From the perspective of a distant observer, the black hole has just emitted a particle. To conserve energy, the particle that fell in must have had negative energy relative to the outside universe. This reduces the black hole's total mass. A single particle is an immeasurably tiny loss, but over astronomical eons, this relentless quantum drizzle causes the black hole to evaporate. This means black holes have a temperature, a concept that was unthinkable before Hawking. A black hole's temperature is inversely proportional to its mass. The larger the black hole, the colder it is and the slower it evaporates. A stellar mass black hole has a temperature of barely a fraction of a degree above absolute zero, making its radiation utterly undetectable against the cosmic microwave background. But a tiny, primordial black hole, if one existed, would be hotter and could evaporate in a spectacular flash of radiation. This discovery also gave black holes an entropy, a measure of their internal disorder. The entropy is proportional to the area of its event horizon, not its volume. This suggests that all the information about what fell into a black hole might be encoded on its two-dimensional surface, an idea known as the holographic principle. This leads directly to the infamous information paradox. If a black hole evaporates completely, what happens to the information that described all the stars, planets, and particles that ever fell in? Quantum mechanics says information must be preserved, but Hawking's calculation suggested it was irretrievably lost. This paradox is a battle cry for a theory of quantum gravity, a conflict where our current laws of physics break down. The Unruh effect provides a related perspective, where an observer accelerating through a vacuum would feel themselves bathed in a warm glow of radiation, a testament to how quantum reality is shaped by one's own motion. Hawking radiation redefines a black hole from a final grave into a dynamic, evolving object, one that may be a temporary phase in the life cycle of the cosmos. If even a black hole is not permanent, what does that say about the stage on which this all plays out? The energy of empty space itself, the cosmological constant, presents a mystery that dwarfs all others. The faint heat of Hawking radiation hints at an energy within the void, but its true scale defies all reason. Our most successful theories predict that the vacuum of space should be boiling with an unimaginable density of energy, a consequence of all those fleeting virtual particles. Quantum field theory calculates this vacuum energy. and the number it produces is astronomically large. Yet when we look out at the cosmos and measure the energy actually driving the accelerated expansion of the universe, what we call dark energy, the value is almost zero. The discrepancy is not a small rounding error. The theoretical prediction is larger than the observed reality by a factor of 1 followed by 120 zeros. This is the cosmological constant problem, and it is the most embarrassing failure of modern physics. Einstein originally introduced the cosmological constant as a fudge factor, a term in his equations of general relativity to allow for a static universe. He later called it his greatest blunder when the universe was found to be expanding. But with the discovery of cosmic acceleration, the constant was resurrected to represent the energy of empty space. The problem is the staggering mismatch between what quantum theory says that energy should be and what our telescopes tell us it is. Renormalization, the mathematical trick physicists use to sweep infinities under the rug in other calculations, utterly fails to resolve this. It is as if we calculated the air pressure in a room should be enough to crush a battleship, but when we walk in, we feel only a gentle breeze. Why is the universe so much closer to nothing than it has any right to be? This profound fine-tuning has led to some radical proposals. Supersymmetry, an elegant theoretical framework, suggests every known particle has a superpartner. If this symmetry were unbroken, the contributions of these partners would perfectly cancel out the vacuum energy, leaving it at zero. But we see no evidence of these superpartners, meaning supersymmetry must be broken, and the cancellation is imperfect, leaving us with the tiny but non-zero value we observe. This connects to another deep puzzle, the hierarchy problem, which asks why the force of gravity is so unimaginably weaker than the other fundamental forces. Another, more philosophical answer is the anthropic principle. This suggests that in a vast multiverse, every possible value of the cosmological constant exists in different universes. We simply find ourselves in one of the rare, finely tuned universes where the vacuum energy is small enough to allow galaxies, stars, planets, and ultimately, life to form. If it were even slightly larger, the repulsive force would have ripped space-time apart before the first stars could ever ignite. The cosmological constant problem is a stark reminder that our two pillars of physics, quantum mechanics and general relativity, are fundamentally at odds. Their clash over the energy of nothingness may be the most important clue we have, pointing toward a deeper theory that can finally tell us why there is something and not nothing, and why that something is so delicately balanced. This struggle to reconcile the very large and the very small forces us to confront the ultimate quantum anomaly, the quest for a single, unified theory of quantum gravity. The staggering mismatch in the energy of empty space forces us to confront another profound imbalance in nature. Why is gravity so unbelievably feeble compared to the other fundamental forces? A simple magnet can lift a paperclip, effortlessly defeating the gravitational pull of the entire Earth. This is the hierarchy problem, a deep puzzle about why the scales of nature are so wildly different. The mass of the Higgs boson, which sets the scale for the electroweak force, is about 250 times the mass of a proton. That seems substantial until you compare it to the Planck scale, the energy at which gravity becomes a powerful quantum force. The Higgs mass should naturally be pulled up to this immense Planck scale by its quantum interactions with every other particle in existence. It is like a tiny boat in a churning ocean, constantly being battered by massive waves that should capsize it instantly. For the Higgs to remain so relatively light, its mass requires a cancellation of these quantum corrections so precise it seems like a cosmic miracle. This fine-tuning strikes many physicists as unnatural, a sign that our current theory is incomplete. One elegant solution is supersymmetry. This theory proposes that every known particle has a hidden superpartner. The quantum contributions from these partner particles would perfectly cancel out the destabilizing effects on the Higgs mass, naturally explaining its lightness. If supersymmetry were real, we should have found these superpartners at the Large Hadron Collider by now. Their absence tells us that if this symmetry exists, it must be broken, meaning the partner particles are far heavier than we had hoped. Another radical idea is that gravity only appears weak because it is not confined to our three-dimensional world. In theories with large extra dimensions, gravity could be leaking out into these hidden realms, diluting its strength from our perspective. On very small scales, gravity might become as strong as the other forces, fundamentally altering our picture of the universe. This search for naturalness is more than philosophical. If supersymmetry is real, the lightest of these superpartners is a perfect candidate for the mysterious dark matter that holds galaxies together. It could also pave the way for a grand unification, where the electromagnetic, weak, and strong forces are seen as different facets of a single sublime force. The hierarchy problem asks why the universe is built on such a lopsided foundation. The answer may lie not in the particles we see, but in a ghostly presence we have yet to find, a hypothetical particle born from another quantum puzzle, the anomaly of Axions. The profound imbalance in the forces of nature points toward a ghostly presence, a particle that may have been hiding in plain sight all along. To understand why we need it, we must look at a different kind of symmetry, one involving the strong nuclear force that glues atomic nuclei together. This force, described by quantum chromodynamics, possesses a curious secret. Its equations allow for a violation of the combined symmetries of charge and parity, known as CP violation. We see this violation clearly in the weak nuclear force, which is why our universe is made of matter and not equal parts matter and antimatter. Yet, for the strong force, no such violation has ever been detected. The theory allows it, but nature forbids it with an unnerving precision. This is the strong CP problem. Why is the strong force so perfectly symmetric? The answer, proposed by physicists Roberto Pexi and Helen Quinn, was not a modification of the rules, but the introduction of a new cosmic field. They suggested a dynamic solution, a field that relaxes to its minimum energy state, naturally cancelling out the CP violating terms in the strong force equations. And just as the Higgs field gives mass to particles, the oscillations of this new field would manifest as a new particle, the action. This hypothetical particle is incredibly light, potentially billions of times lighter than an electron, and it interacts with ordinary matter only with the faintest of whispers. This profound shyness makes the action a perfect candidate for the universe's missing mass for dark matter. It could be streaming through this room right now, a ghostly wind of particles that collectively outweigh all the stars and galaxies we see. How could we possibly detect such an elusive thing? Ingenious experiments are hunting for them. The Action Dark Matter Experiment, or a DMX, uses a powerful superconducting magnet inside a cryogenic cavity. The theory suggests that in the presence of a strong magnetic field, an action could convert into a very faint microwave photon. A DMX is essentially a giant, ultra-sensitive radio receiver, tuned to listen for the faint whisper of an action converting into light. We are also searching for them in the sky. Actions could be produced in the core of our sun, and telescopes on Earth are looking for the specific kind of X-ray signal that would result from these solar actions converting back into photons in the magnetic field of our own planet. If we find it, the action would solve two of the greatest mysteries in physics at once. It would explain the strange symmetry of the strong force and reveal the identity of the dark matter that shapes the cosmos. But this ghostly particle is not the only relic predicted by our theories of unification. The same grand theories that hint at Axions also predict a magnetic phantom, a particle with a single, isolated pole, an anomaly known as the magnetic monopole. A magnet, forever bound as a pair, defines everything from a child's toy to the Earth's own protective shield. Yet the deepest theories of physics insist there should be a loner, an isolated north or south pole forever separated from its opposite. This is the phantom of the magnetic monopole, a particle that should exist but has never been found. Our entire understanding of magnetism, enshrined in Maxwell's elegant equations, is built on the idea of the dipole. Break a bar magnet in half, and you do not get a separate north and a south. You get two new magnets, each with its own pair of poles. The equations seem to forbid a solitary pole from existing. But the theoretical physicist Paul Dirac saw a crack in this logic. He demonstrated that if even a single magnetic monopole existed somewhere in the universe, it would instantly explain one of nature's deepest mysteries, the quantization of electric charge. Why does every electron carry the exact same, identical charge? Dirac showed that the presence of a monopole would force electric charge to come in discrete, indivisible packets, creating a beautiful and profound symmetry between electricity and magnetism. This idea was revived and expanded in the grand unified theories of the 1970s. Physicists like Gerard T. Hooft and Alexander Polyakov showed that in these theories, which merge the electromagnetic, weak, and strong forces, monopoles are not just possible, they are inevitable. They emerge not as fundamental point-like particles, but as solitons, stable, particle-like kinks in the fabric of a field, much like a knot in a rope that cannot be untied. This presents cosmology with a glaring problem. If grand unification is correct, the early universe should have been flooded with these magnetic monopoles. Their density should be so high that they would dominate the mass of the cosmos today. The fact that we do not see them is one of the strongest arguments for the theory of cosmic inflation. This period of hyper-expansion in the universe's first moments would have stretched space-time so thin that it would have diluted the monopoles to near invisibility, sweeping them far beyond our observable horizon. The hunt for this phantom particle continues. Scientists scan ancient mica crystals for the telltale damage trails a heavy, charged monopole would leave. They search through data from cosmic ray detectors and listen for the distinctive signal a monopole would create in massive loops of superconducting wire. The Large Hadron Collider itself is a hunting ground, hoping to create one in a violent collision. Finding just one would be a revolution. It would be direct evidence for grand unification and could provide crucial support for string theory, which also predicts their existence. It would confirm that the deepest symmetries of nature are written in a language of unity, not separation. The very fact that we have not found them forces us to question the stability of the matter that makes us. If forces can unify, then the very protons at the heart of every atom may not be eternal, leading us to the next unsettling possibility, the decay of the proton. Every proton in your body was once thought to be eternal, but the grand theories that seek to unify the cosmos whisper a different, unsettling truth. These protons, the very bedrock of the atoms that build our world, may not be stable. They could, over timescales so vast they defy comprehension, spontaneously decay into lighter particles. This is the startling prediction of grand unified theories, which propose that the electromagnetic, weak, and strong forces were once a single, sublime force in the universe's first moments of existence. For this decay to happen, a fundamental rule must be broken, the conservation of baryon number. This law states that the total number of heavy particles like protons and neutrons must stay constant. It is why in our everyday world matter seems so permanent. Grand unification shatters this principle, suggesting that the deep distinction between a quark, the building block of a proton, and a lepton, like an electron, is an illusion. They are simply different facets of the same underlying entity. The decay process itself is mediated by hypothetical, immensely heavy particles called X-bosons. Inside a proton, one of its quarks could be transformed by an X-boson, causing the entire structure to disintegrate into a shower of lighter particles, like a positron and a pion. How long would we have to wait to see such an event? Theoretical models suggest a half-life of around 10 to the 34 years, a number so large it dwarfs the current age of the universe. To hunt for this incredibly rare event, scientists have built the most pristine detectors on Earth. The Super Kamiok and Observatory in Japan is a colossal tank holding 50,000 tons of ultra-pure water, surrounded by thousands of sensitive light detectors. It watches for the faint flash of Cherenkov radiation that would signal a single proton decaying deep within its heart. So far, the protons have held firm. Not a single confirmed decay has been seen, which tells us that if protons do decay, their lifetime must be even longer than our current limits. This null result is not a failure but a guide. It constrains the possible versions of grand unified theories, ruling out the simplest models and pushing us toward more complex ideas like supersymmetry or extra dimensions. The implications of proton decay reach to the very beginning and the ultimate end of everything. In the first instance after the Big Bang, a slight asymmetry in the decay of primordial X-bosons could have tipped the scales, creating just a little more matter than antimatter. This is a leading candidate to explain why we live in a universe of matter, rather than one that annihilated itself into pure radiation. And for the distant future, if protons do decay, it means that all matter is ultimately transient. Trillions upon trillions of years from now, long after the last stars have burned out, the very atoms of dead galaxies and planets will slowly, silently evaporate into light. The solid ground of existence would literally fade away. This profound connection between the stability of matter and the evolution of the cosmos forces a question about another seemingly stable particle, one that has already proven it can shift its identity, the ghostly neutrino. The very protons that build our world might be transient, but there is another particle that is a master of transformation, shifting its identity as it flies through the cosmos. Neutrinos are ghostly particles that stream through you by the trillions every second, interacting with almost nothing. For a long time, we thought they were massless, mere spectral bystanders in the cosmic drama. Then we noticed something impossible. An electron neutrino born in the heart of the Sun could, by the time it reached Earth, have changed into a muon neutrino or a tau neutrino. This is the bizarre phenomenon of neutrino oscillation, a quantum tango where a particle seamlessly morphs between three distinct flavors as it travels. The discovery solved a decades-long mystery known as the solar neutrino problem. Experiments built to detect neutrinos from the Sun, like Ray Davis's famous Homestake mine detector, kept finding only a third of the number predicted by solar models. The neutrinos were not missing. They were simply changing into flavors the detector could not see. This realization, which earned the Nobel Prize in 2002, shattered a key pillar of the original standard model of particle physics. Massless particles, according to that model, must travel at the speed of light and experience no time, making such a change impossible. The very fact that neutrinos oscillate is direct, undeniable proof that they have mass. How does this work? Think of a neutrino's flavor, like electron or muon, not as its true identity, but as a mixture of its possible mass states. It is like having 3 differently weighted coins constantly shuffling in your hand. The neutrino travels through space as a quantum superposition of these different mass states. Because each mass state travels at a slightly different speed, the mixture evolves, and the probability of detecting a particular flavor changes rhythmically over distance. This intricate mixing is mapped by a complex mathematical object called the Pontecorvo-Makee-Nakagawa-Sakata matrix. The implications are staggering. This tiny mass, a mere whisper compared to the electron, demands new physics. One compelling idea is the seesaw mechanism, which proposes that the familiar, lightweight neutrinos we see have incredibly heavy, sterile partners, perhaps existing in hidden dimensions. These heavy partners would pull down the mass of the light ones, explaining their profound feebleness. The study of these oscillations is also our best window into a potential cosmic asymmetry. Just as matter slightly outweighed antimatter in the early universe, neutrinos and antineutrinos might oscillate at different rates. This difference, known as CP violation in the lepton sector, could be the very engine that drove the creation of all the matter we see, a process called leptogenesis. To catch these shape-shifting particles in the act, scientists build colossal detectors deep underground. The ice cube experiment, for example, uses a cubic kilometer of pristine Antarctic ice as its detector, watching for the rare flashes of light produced when a neutrino finally interacts. Each oscillation they measure is a clue not just about the neutrino, but about the fundamental symmetries that shaped our universe. If a particle can be multiple things at once, its true nature defined only by its journey, what does that say about the reality we perceive? This quantum ambiguity brings us back to a foundational conflict, the EPR paradox, which first challenged the very meaning of locality and reality. Einstein's discomfort with quantum mechanics culminated in a brilliant intellectual assault. In 1935, together with Boris Podolsky and Nathan Rosen, he crafted a thought experiment designed to prove that the theory was incomplete. The EPR paradox begins with a simple, seemingly reasonable assumption. If you can predict the value of a physical property with absolute certainty without in any way disturbing the system, then that property must correspond to an element of reality that exists independently of any measurement. Now take 2 particles born from a common source, their properties forever entangled. According to quantum mechanics, neither particle has a definite position or momentum until one is measured. But the EPR reasoning went like this. Measure the position of particle A, and you instantly know the exact position of particle B, no matter how far away it has traveled. Alternatively, you could choose to measure the momentum of particle A, and thereby know the exact momentum of particle B. Since you could predict either property without touching particle B, both its position and its momentum must be real, definite elements of its reality all along. Quantum mechanics, which says these properties are indefinite until measurement, must therefore be an incomplete description of the world. There must be some deeper layer of hidden variables that determine these outcomes in a local, sensible way, without any spooky action at a distance. For 3 decades, this stood as a powerful argument for a more intuitive, classical reality lurking beneath the quantum weirdness. Then came John Bell. He showed that if local hidden variables existed, the statistical correlations between the entangled particles would have to obey certain mathematical limits, now called Bell inequalities. Quantum mechanics, with its spooky correlations, blatantly violates these limits. The subsequent experiments, from Elaine Aspect's pioneering work to recent loophole-free tests, have all delivered the same verdict. The Bell inequalities are broken. The universe does not operate on local hidden variables. The eerie connectedness of entanglement is real. This means that the very idea of separateness is an illusion. The two particles are not two independent entities. They are a single, non-separable system, a unified whole even when separated by light years. This shatters our classical notion of objectivity. Properties like position and spin are not inherent to a particle waiting to be revealed. They are created by the very act of measurement and the context of the entire entangled system. The reality of one particle is inextricably linked to the reality of the other, forcing us to abandon the idea of a universe of independent objects. If observation plays such a powerful role in defining reality, what happens if we never stop looking? This relentless gaze leads us to one of the strangest quantum anomalies of all, a phenomenon where constant observation can freeze reality in its tracks. Constant observation can freeze time itself for a single quantum particle. This is the quantum Zeno effect, a bizarre phenomenon where the simple act of repeatedly looking at a system can prevent it from ever changing. It is the scientific version of the old saying, "A watched pot never boils." In the quantum world, when a system is left alone, its wave function evolves smoothly, spreading out and exploring different possibilities, like an unstable particle preparing to decay. But the moment you measure it, you force it to collapse back into a definite state, resetting its internal clock. If you measure it again and again with relentless frequency, the system simply does not have the time to evolve. It becomes trapped in its initial state, frozen by the glare of observation. This idea draws its name from the ancient Greek philosopher Zeno, who proposed paradoxes where motion was an illusion, like an arrow that must first cross half the distance to its target, then half of the remaining distance, and so on forever, seemingly never arriving. The quantum version, formalized by physicists Misra and Sudarshan, reveals this is not just a philosophical puzzle. It is a real physical consequence of how measurement interrupts the natural flow of a quantum state. We have seen this in the laboratory with trapped ions. By repeatedly checking whether an ion is still in its ground state, researchers can dramatically suppress the probability that it will jump to a higher energy level. The ion, under constant surveillance, obeys by not moving. This has a profound and immediate application in the fragile world of quantum computing. Qubits are notoriously delicate, their precious superpositions constantly threatened by decoherence. The quantum Zeno effect offers a clever defense. By periodically and gently measuring a qubit, we can actively pin it in its desired state, protecting its quantum information from the environmental noise that seeks to destroy it. It is a form of quantum guardianship, using observation not to collapse reality but to preserve it. This turns the traditional measurement problem on its head. We usually think of observation as the act that destroys quantum magic. Here, it becomes the tool that sustains it. So what does this say about the power of a gaze? It suggests that in the quantum realm, reality is not just altered by observation, but can be actively held in place by it. The connection between what we see and what is becomes a dynamic dance, one that leads us to another mystery where what matters is not the force itself, but the landscape it creates. The path an electron takes is shaped by a ghostly presence. In the everyday world, a force must touch an object to push or pull it. A magnet moves a paperclip because its field reaches out and acts upon the metal. But in the quantum realm, an electron can be guided by a force it never feels, a whisper from a field it never enters. This is the Aharonov-Bohm effect, a profound anomaly where the stage itself directs the actors, even when the stage appears completely empty. Physicists Yakir Aharonov and David Bohm predicted that a charged particle, like an electron, is sensitive not just to magnetic fields, but to the underlying electromagnetic potential from which those fields arise. Imagine a long, perfect solenoid, a coil of wire that contains a powerful magnetic field locked entirely within its core. Outside this solenoid, the magnetic field is precisely zero. Now fire a beam of electrons so that it splits in two, with one stream passing on either side of this shielded cylinder before recombining. Classically, since the electrons never entered the magnetic field, nothing should happen. Their paths should be identical, yet when the two beams meet, they create an interference pattern that has shifted. The peaks and troughs have moved. The electrons, behaving as waves, have acquired a phase shift simply by encircling a region where a magnetic field resides, even though they were never exposed to it. This shift is dictated by the vector potential, a mathematical description of the electromagnetic landscape. In quantum mechanics, this potential is not just a convenient calculation tool. It is physically real, leaving its imprint on the electron's wave function. This was confirmed through stunningly precise experiments using electron interferometers, where the predicted phase shifts were observed exactly as theorized. The implications are staggering. It suggests that what is fundamental in our universe is not the force field you can measure, but the potential that defines it. The electron is not a local object responding only to its immediate surroundings. It is aware of the global topology, the shape of the space it travels through. This deep connection to topology is why the Aharonov-Bohm effect is a cornerstone of our understanding of geometric phases, where the history of a quantum system's path in an abstract space matters more than the details of the journey. It underpins the physics of the quantum Hall effect, where electrons flowing along the edge of a material remember the topological character of the bulk. In the quest to build quantum technologies, this effect is not merely a curiosity. It is a design principle, suggesting ways to control quantum states by engineering the potentials they experience, rather than by applying brute forces. So we are left with a universe where influence transcends direct contact. If an electron can be guided by an invisible potential, what other unseen forces are constantly at work, shaping reality from the shadows? This question pulls our gaze to the emptiest space imaginable, where the void itself pushes back. Two perfectly smooth plates, suspended in an absolute vacuum, will defy all classical expectation and gently drift together. This is not magic, but the undeniable signature of a seething, active void. The Casimir effect is a force born from nothingness, a tiny but measurable push that occurs when you bring two neutral metal plates extremely close together. In the emptiness of space, virtual particles are constantly flickering in and out of existence, a quantum foam of possibilities. Between the plates, only certain wavelengths of these fluctuations can fit, like specific musical notes resonating between two walls. Outside the plates, all wavelengths are possible. This creates a pressure imbalance. The greater cacophony of virtual particles pushing on the outside of the plates overwhelms the quieter activity between them, forcing the plates together. Hendrik Casimir predicted this ghostly force, and we have since measured it with stunning precision in the laboratory. This is not just a theoretical curiosity. It is direct physical proof that the vacuum of space is not passive emptiness, but a vibrant sea of zero-point energy, the lowest possible energy state of a quantum field. To even calculate the strength of this force, physicists must use sophisticated mathematical tools like Z, a function regularization, to tame the infinities that naturally arise from summing all these possible vacuum modes. The Casimir effect is more than a cosmic demonstration. It is a real-world engineering challenge in the realm of the incredibly small. In the design of micro-electromechanical and nano-electromechanical systems, or MEMS and NEMS, these tiny Casimir forces can cause components to stick together, a phenomenon known as stiction that designers must actively work to overcome. On a grander scale, this vacuum energy is a leading candidate for the mysterious dark energy accelerating the expansion of the entire cosmos. So what does this teach us about empty space? It reveals that nothing is ever truly empty. The void itself has a structure, a personality, and a palpable energy that can push and pull on the objects within it. If the mere structure of empty space can create a measurable force, what happens when we move through that space at an incredible rate? This question leads us to a related but even stranger phenomenon, where motion itself conjures heat from the quantum void. Motion itself can conjure heat from the void. An astronaut floating in the deep emptiness of interstellar space would feel only the profound cold of the vacuum. But if that same astronaut were to fire their engines and accelerate at a tremendous rate, their instruments would suddenly detect a warm glow of radiation, a bath of real particles filling the space around them. This is the Unruh effect, a stunning prediction where acceleration makes the vacuum boil. Proposed by physicist William Unruh, this phenomenon reveals that the concept of a particle is not an absolute truth of the universe, but depends entirely on the state of the observer. An inertial observer drifting peacefully sees nothing but empty space. An accelerating observer hurtling through that same nothingness finds themselves immersed in a thermal bath. The temperature of this ghostly radiation is directly proportional to the acceleration. To feel even a single degree of warmth above absolute zero, you would need to accelerate at a quadrillion times the force of gravity on Earth, a rate so extreme it makes direct experimental verification incredibly challenging. How can motion alone create particles from nothing? The key lies in Einstein's equivalence principle, the same idea that tells us acceleration feels indistinguishable from gravity. In this case, the acceleration mimics a gravitational field, and this alters how the observer's detectors couple with the quantum fields of the vacuum. To describe this from the accelerating observer's point of view, physicists use Reindler coordinates, which divide spacetime into distinct regions, much like an event horizon. Some parts of the universe become forever inaccessible, and it is this new horizon that gives rise to the thermal radiation, in a beautiful parallel to how a black hole's event horizon produces Hawking radiation. This forces a profound philosophical shift. There is no single, objective answer to the question of what particles exist in a given region of space. Reality, at its most fundamental quantum level, is observer-dependent. Your motion, your frame of reference, actively participates in determining what you perceive as real. This idea resonates through cosmology, suggesting that the thermal history of our universe might be intertwined with its expansion and acceleration. If the very existence of particles is not a universal fact, but a personal experience shaped by your path through space-time, what does that mean for information itself? When something falls into a black hole, is that information truly lost, or is it preserved in some way we cannot yet see? This question brings us to the most heated debate in modern physics, the black hole information paradox. The most fundamental laws of physics insist that information can never be truly destroyed. You could burn a book, scattering its atoms and energy, but in principle, every single letter could be recovered from the ashes and the heat. This principle of unitarity is the bedrock of quantum mechanics, yet a black hole presents a terrifying exception. When matter falls in, every detail, every bit of information that described a star, a planet, or a person seems to vanish from our universe, sealed behind an event horizon. Stephen Hawking's own calculations showed that the radiation leaking from a black hole is purely thermal, a featureless heat carrying no information about what created it. If the black hole evaporates completely, that information is irrevocably lost, a direct violation of quantum law. This is the black hole information paradox, a battle cry for a deeper theory of reality. How can we resolve this war between gravity and quantum mechanics? One radical idea is the holographic principle. It suggests that all the information about what fell into the black hole is not stored in its hidden volume, but is instead encoded on its two-dimensional surface, the event horizon, like a cosmic fingerprint. Every bit of information that crosses that boundary is painted onto this surface, and as the black hole evaporates, this information is slowly and chaotically released back into the universe. The work of physicists like Leonard Susskind and Gerard T. Hooft gave this idea mathematical form, showing how a world with gravity could be equivalent to a quantum theory without gravity operating on its boundary. This concept is dramatically realized in the AD/CFT correspondence from string theory, a precise duality where a gravitational universe is perfectly described by a conformal field theory on its edge. The journey of this information is described by the Page curve, a graph devised by Don Page. It shows that initially, as the black hole evaporates, the radiation it emits is random and carries little information. But after a point known as the Page time, the radiation begins to carry away the original information, and the entanglement between the black hole and the earlier radiation shifts dramatically. This intricate dance of entanglement entropy is the key to unlocking the paradox. Another, more violent proposal is the firewall hypothesis. It suggests that rather than a smooth passage through the event horizon, an infalling observer would encounter a blazing wall of energy, a firewall created by the breakdown of entanglement across the horizon. This would destroy any object before it could enter, preserving information but shattering our classical picture of a black hole's interior. These are not just abstract games. They force us to ask what really happens at the edge of a black hole. Is the universe fundamentally two-dimensional, with our perception of three dimensions merely a holographic projection? If information is not lost but transformed, then reality itself might be a kind of cosmic code. This idea that the universe is a projection from a lower dimensional surface is the next great anomaly, one that redefines the nature of space and dimension. Our universe might be a magnificent illusion, a cosmic hologram of breathtaking complexity. The information needed to describe every star, every planet, and every one of us within a volume of space could be entirely encoded on its two-dimensional boundary, painted onto the surface that contains it. This is the holographic principle, a radical idea born from the thermodynamics of black holes. When Jacob Bekenstein and Stephen Hawking discovered that a black hole's entropy, its hidden information, is proportional to the area of its event horizon, not its volume, it hinted at a profound secret. The maximum information any region of space can hold is not defined by how big it is inside, but by the size of its surface area. Gerard T. Hooft and Leonard Susskind took this stunning clue and proposed that this is not just a property of black holes, but a fundamental principle of the universe. We are all potentially living inside a hologram, where the three-dimensional world we experience is a projection from a vast, complex code written on a distant, two-dimensional surface. The most concrete realization of this mind-bending idea comes from string theory, in a discovery known as the AD/CFT correspondence. This provides a precise mathematical dictionary. It states that a theory of gravity operating in a hypothetical universe with a certain shape, called anti-de Sitter space, is completely equivalent to a conformal field theory, a quantum theory without gravity, that lives on its lower dimensional boundary. A calculation involving black holes and gravitational forces in the bulk of the universe can be perfectly translated into a calculation involving particles and quantum interactions on its edge. This is not just a philosophical curiosity. It has become a powerful tool, allowing physicists to solve difficult problems in nuclear physics by translating them into simpler gravitational problems in a higher dimensional holographic world. The implications are staggering. If the holographic principle is true, then space-time and gravity themselves are not fundamental. They are emergent phenomena arising from a vast network of quantum information entangled on a lower dimensional surface. The solidity of the world around you, the very force that holds your feet to the ground, might be a collective consequence, much like the wetness of water emerges from the interactions of countless individual molecules. This forces us to ask a deep question about the nature of our own reality. Are the three spatial dimensions we move through every day nothing more than a convenient, albeit powerful, illusion? If our universe is a holographic projection, then what is the nature of the original source? This line of thought inevitably pulls our gaze outward to the possibility that our cosmic hologram may be just one of countless others in an unfathomably vast multiverse. Our reality could be a single page in an infinite cosmic library. This is the multiverse, a vast ensemble of universes, each with its own unique set of physical laws and constants. In this breathtaking view, our universe is not special or fine-tuned by design, but simply one of countless possibilities where the numbers happen to be right for galaxies, stars, and life to emerge. This idea flows naturally from our most ambitious theories. The concept of eternal inflation suggests that the rapid expansion of the early universe never truly stopped everywhere. Instead, it continues eternally in a background sea, with individual pockets stopping their inflation to form isolated bubble universes, each a separate cosmos with its own physics. String theory adds another layer to this landscape, predicting a staggering number of possible stable configurations for the extra dimensions it requires, perhaps 10 to the 500 different versions of vacuum energy and physical laws. This directly addresses the cosmological constant problem. The value we observe is not a mysterious, finely tuned miracle. It is simply the value we ended up with in our particular bubble, a random draw from a cosmic lottery where most universes are sterile and empty. This framework, advanced by thinkers like Andre Linde, offers a powerful, if speculative, explanation for why our universe seems so perfectly suited for life. Yet it introduces its own profound puzzles, like the measure problem. In an infinite multiverse, how do we assign sensible probabilities to anything? If every possible event occurs in some universe, how do we determine what is likely or unlikely in our own? This idea finds a strange echo in the quantum realm through the many worlds interpretation. In this view, every quantum decision, every superposition that collapses in the Copenhagen interpretation does not collapse at all. Instead, the entire universe splits. In one branch, the radioactive atom decays and the cat dies. In another, it does not and the cat lives. Both realities are equally real, constantly branching from every quantum event, creating an ever-expanding tree of parallel histories. So the multiverse may exist on two scales, the cosmological and the quantum, a dizzying tapestry of cosmic and personal possibilities. But if every possibility is realized somewhere in this vast ensemble, what does that say about the one direction we all experience, the relentless and irreversible flow of time? The relentless expansion of the multiverse suggests a cosmos where every possibility unfolds, yet our own experience is pinned to a single, irreversible direction. This is the great arrow of time, a fundamental asymmetry woven into our perception of reality. the laws of physics themselves, from Newton's mechanics to quantum electrodynamics, are almost perfectly symmetric in time. If you were to reverse the direction of time in their equations, they would still hold true. A movie of two planets orbiting each other or of two electrons colliding would look perfectly natural played backwards. So why does our universe only move forward from a state of order to one of increasing disorder? This is the puzzle of time symmetry breaking, and its roots may lie in the very first moment of everything. The second law of thermodynamics gives us the language for this, stating that the entropy or disorder of an isolated system always increases. But why was the entropy of the early universe so incredibly low to begin with? This is the past hypothesis, the idea that our cosmic story started in a state of exquisite, improbable order. The Big Bang was not a chaotic explosion, but a remarkably smooth and organized event. From that pristine starting point, the only way to go was towards a messier, higher entropy state, and that inevitable slide gives us the feeling of time's forward march. This cosmic initial condition is deeply mysterious, and quantum effects may have been the sculptor. The process of quantum decoherence, which constantly collapses superpositions into definite states, provides a steady source of irreversibility, a constant ticking of the cosmic clock. In the quest for quantum gravity, the Wheeler-DeWitt equation famously describes a universe without time, a frozen landscape where past, present, and future coexist. Time, in this view, is not a fundamental stage but an emergent property, a story we tell about change and correlation within a timeless whole. This profound asymmetry even connects to the particle world. The same CP violation that may explain our matter-dominated universe also introduces a microscopic arrow of time. If the laws treating matter and antimatter were perfectly symmetric, they would be time-symmetric as well. The fact that they are not suggests that the arrow of time we feel on a cosmological scale is linked to the very particles that build our bodies. So the flow of time may be the ultimate emergent phenomenon, a story written by the universe's journey from a unique beginning to an uncertain future. This forces a staggering question. If time is not fundamental but emerges from a deeper, timeless quantum reality, what other cosmic truths are we missing? This search for the origin of time's arrow leads us directly to the final frontier, the quest to unite the very large and the very small in a single theory of quantum gravity. The final frontier of physics lies in the heart of a black hole, where the laws of the cosmos break down. We have two magnificent pillars of science. Quantum mechanics describes the universe of the very small with breathtaking accuracy, while general relativity explains the force of gravity and the large-scale structure of the cosmos with equal success. But these two theories speak different, mutually incompatible languages. They cannot both be correct at the center of a black hole or at the moment of the Big Bang, where density becomes infinite in a point called a singularity. Quantum gravity is the quest for a single theory that can unite them, to describe the fabric of reality itself at its most fundamental level. This is not merely an academic exercise. It is a search for the operating system of the universe. At the tiniest conceivable scale, the Planck length, which is about 10 to the negative 35 meters, space-time itself may not be smooth and continuous. It might be quantized, composed of discrete, indivisible grains, much like a digital image is made of pixels. Different approaches attempt to map this unknown territory. Loop quantum gravity proposes that space is woven from networks of intersecting loops, a spin foam where the very concepts of before and after can dissolve. String theory, another leading contender, suggests that the fundamental objects are not point particles but tiny, vibrating strings. Their different vibrational modes give rise to every particle and force we see, and they require extra dimensions of space to maintain their mathematical consistency. A key challenge in this quest is background independence. General relativity tells us that space-time is dynamic, bending and warping in response to mass and energy. A true theory of quantum gravity must not treat space and time as a fixed stage on which physics plays out, but must make the stage itself a dynamic part of the play. The holographic principle we explored earlier is a powerful clue emerging from this struggle. It suggests that the information within a volume of space is encoded on its boundary, hinting that our experience of a three-dimensional world may be a projection from a deeper, two-dimensional reality. The thermodynamics of black holes provides another crucial testing ground. The fact that a black hole has entropy and temperature points directly to an underlying quantum structure for spacetime. As our observational tools grow sharper, we may find evidence. Subtle imprints of these spacetime grains could potentially be detected in the polarized light from the cosmic microwave background, or in the faint whispers of gravitational waves from colossal cosmic events. A successful theory of quantum gravity would not just resolve paradoxes, it would take us to the very origin of everything, to the first moment of time, and answer the ultimate question of why there is a universe at all. This search for the quantum fabric of spacetime compels us to look for its signature in the most dominant, yet invisible, component of our cosmos, the mysterious nature of dark matter. The fabric of spacetime may be woven from quantum threads, but a deeper mystery holds our galaxies together. All the stars, planets, and cosmic dust we can see account for less than 20% of the matter that must exist. The rest is a ghost, an invisible presence whose gravity sculpts the cosmos yet refuses to be seen. This is the quantum enigma of dark matter, a substance that appears to be made of unknown particles that interact with our world through gravity alone, ignoring light and matter with profound indifference. Its nature is one of the greatest anomalies in physics because its gravitational effects are undeniable, warping the paths of light and holding galaxies in a cosmic grip, while its particle identity remains a total mystery. We have built incredible experiments to catch this ghost, deep underground in abandoned mines shielded from cosmic rays. Detectors like LUX and Xenon wait in the utter dark. They are filled with ultra-pure liquid xenon, a vast target for a single, hoped-for event. The idea is that a dark matter particle, perhaps a WIMP or weakly interacting massive particle, might, on a very rare occasion, bump into the nucleus of a xenon atom, producing a tiny flash of light and a wisp of free charge. So far, the silence is deafening. We have not heard that whisper, which tells us that dark matter is even more elusive than we imagined. This forces us to extend our thinking beyond the standard model of particle physics. The most promising ideas come from theories like supersymmetry, which predicts a whole shadow zoo of superpartner particles, the lightest of which could be the very WIMP we are searching for. Or in theories with extraspatial dimensions, dark matter could be a particle that moves freely in these hidden realms, only brushing against our three-dimensional world through gravity. Even more exotic is the action, a particle born from a different quantum puzzle, which could be so light and numerous that it forms a coherent wave flowing through the galaxy. The evidence for this invisible matter is etched into the oldest light in the universe. The subtle patterns in the cosmic microwave background, the afterglow of the Big Bang, show a specific distribution of hot and cold spots. This pattern could only have formed if a gravitating, non-interacting substance was present to pull on the primordial plasma, seeding the structures that would one day become galaxies. What if dark matter has a rich, hidden quantum life of its own? Some theories suggest it could have weak self-interactions, a faint force that causes dark matter particles to scatter off one another, smoothing out the dense cores of galaxies. And in its most ethereal form, if the dark matter particle is a boson, it could undergo a quantum phase transition on a galactic scale. Billions of these particles could condense into a single, gigantic wave, a Bose-Einstein condensate that forms an invisible quantum halo around an entire galaxy. Solving this mystery would do more than just identify a missing component of the cosmos. It would fling open a door to an entirely new realm of physics, revealing particles and forces that have operated in the shadows since the beginning of time. This profound connection between the quantum world and the cosmic scale inevitably pulls our gaze inward to the most personal anomaly of all, the quantum nature of the mind that contemplates it. Our own awareness might be a quantum phenomenon. The idea that consciousness itself is rooted in the bizarre rules of the quantum world is perhaps the most speculative and profound anomaly of all. This is the hypothesis of quantum consciousness, a theory suggesting that the very processes of thought, cognition, and free will are not merely the product of classical neural firing, but involve delicate quantum effects within the brain's architecture. The physicist Roger Penrose, together with anesthesiologist Stuart Hameroff, proposed a specific mechanism called orchestrated objective reduction. In this view, the neurons in our brain contain structures called microtubules, which act as the cell's scaffolding. Penrose and Hameroff suggest that these microtubules are not just passive beams, but can host quantum superpositions. A single thought could be a complex quantum computation happening across these tiny networks. The collapse of this superposition, the moment a possibility becomes a definite reality, would not be triggered by a random interaction, but by a precise threshold related to the mass of the system, a process orchestrated by the brain's biological structure. It is this moment of objective collapse that they propose is the physical basis for a moment of conscious experience. The implications of this are staggering. It could provide a scientific framework for free will, where our choices are not predetermined by a chain of classical cause and effect, but emerge from a quantum process of possibility and selection. It would mean that our minds are not just computers made of meat, but are deeply integrated with the fundamental quantum fabric of the universe. Yet this idea faces immense, and many would say insurmountable, challenges. The brain is a warm, wet, and chaotic place. We have seen how quantum coherence, that fragile state of being in multiple states at once, is destroyed in an instant by random interactions with the environment. How could such delicate quantum dances possibly survive for even a fraction of a second in the bustling, biochemical storm of a living brain? Critics argue that any quantum superpositions in microtubules would decohere far too quickly to have any meaningful role in neural processes. The evidence for quantum consciousness remains elusive and highly controversial within the scientific mainstream. But if it were true, it would force a revolution that extends beyond biology. It would suggest that to create a truly conscious artificial intelligence, we might need to build quantum minds, machines capable of harnessing superposition and entanglement to generate genuine awareness. This final anomaly brings our journey full circle, from the strange behavior of a single particle to the inner workings of the mind that observes it. Each of these 30 quantum anomalies, from entanglement to the holographic principle, chips away at our classical intuitions. They reveal a universe that is not a collection of separate objects, but a deeply interconnected, probabilistic, and participatory whole. The solid ground beneath our feet, the relentless flow of time, the very nature of our own thoughts, all may be illusions born from a deeper quantum reality. The greatest mystery is no longer just out there in the cosmos, but within the consciousness that strives to understand it. These 30 threads of quantum mystery weave a single, breathtaking tapestry. The ghostly connection of entanglement, the shape-shifting dance of neutrinos, the faint heat from a black hole's edge, and the invisible pull of dark matter are not isolated curiosities. They are different facets of a reality far more fluid, interconnected, and wonderful than the rigid clockwork universe of classical physics. Each anomaly is a puzzle that refuses to fit, yet this refusal is what drives our greatest leaps forward. The same non-locality that baffled Einstein is now the engine of unbreakable quantum cryptography. The delicate superpositions we struggle to protect in ultra-cold labs are the heart of computers that could one day solve problems we cannot yet even conceive. Our struggle to understand the quantum vacuum and dark energy is reshaping our entire cosmic story, pushing the boundaries of cosmology and philosophy. When we step back and look at them together, patterns begin to emerge. The universe seems to whisper a new set of rules, where information is more fundamental than matter, where space-time is not a stage but an emergent property of a deeper holographic code, and where non-locality suggests a profound unity beneath the illusion of separation. This is not a picture of a broken reality, but of one that is far richer and more complex than we ever imagined. It encourages us to find beauty in uncertainty, to see the potential in the unknown. The greatest legacy of these quantum mysteries may not be a single equation, but the inspiration they provide for the next generation of explorers. What new technologies will they build from these insights? What cosmic secrets will they unlock when they finally learn to speak the language of this deeper reality? Our journey through 30 quantum anomalies reveals a cosmos far stranger than any fiction. We have wandered from the spooky connection of entangled particles to the shape-shifting dance of neutrinos, from the faint heat of Hawking radiation to the invisible grasp of dark matter. Each of these phenomena is a crack in the foundation of our classical reality, a place where the impossible becomes not just possible but fundamental. They are not flaws in the universe, but clues pointing toward a deeper, more interconnected, and more wonderful truth. Our understanding is not a final picture, but a living, evolving process, forever driven by the engine of curiosity. The physicist Richard Feynman captured this perfectly when he remarked, "I think I can safely say that nobody understands quantum mechanics. This is not a statement of defeat, but a celebration of the endless mystery that lies at the heart of everything." Let this exploration be a spark, igniting your own wonder and encouraging you to look at the familiar world with profoundly unfamiliar eyes. We want to hear which of these anomalies captured your imagination. Was it the ghostly influence of non-locality, or the holographic possibility that our reality is a projection? Share your thoughts in the comments below and subscribe to join us on our next deep dive into the cosmos. Together, we can continue to unravel the grandest secrets of